So what we're going to do now is look at the rules for differential calculus. We're going to end up with a table of rules for you to refer to. And like the rules for laws of indices, it'll be handy if you've got those on a separate piece of paper so you can just use them. Eventually you'll get to know them. I'm going to do it by introducing the idea of when we might use calculus by looking at a problem. And so we'll go through that together. And then we'll look at some examples. Those examples will appear on the video clip, and we'll do those all together, and then I'll give you some time to have a go at some from the textbook. Okay? So that's the plan. So these rules then. Here's a problem that it's taken from the textbook, actually. You'll find it if you look in there. It's in the algebra section, but we're applying it to calculus. If you have a piece of sheet metal, you can cut it up to make an open-top box. So if you're going to open up this box, what you need to do is to cut out the corners so you can then turn the flap up and make the sides to the box. You can make the box very wide and shallow when x is small, or you can make the box narrow and quite high by increasing the value of x. So I can change the value of x and make the box, you know, tall and narrow, or short, wide and rather flat. We can come up with an expression for the volume of the box. So if we look on here, this is part done for you. If you look at what's there in front of you, if x is this distance here that we're going to cut out, then this distance here is 20 minus 2x. And is that clear why it's 20 minus 2x algebraically? That expression gives us this distance from here to here. The whole width of this sheet of metal is 20 centimeters, and so I've got to subtract from that 20 two lots of x, because there's the two ends there to take off. So 20 minus 2x expresses that length. Agreed? And similarly, 12 minus 2x expresses the width of the box. What would the height of the box be? Which in this case will just be x. Right, so the height of the box will be x. So write down an expression for the volume. How would we work out the volume of the box? And what would that be in terms of what's written on here? I'll just leave you a second to have a go at writing that down. Write down an expression for the volume of the box. So an expression for the volume of the box would be length, which in terms of the algebra is 20 minus 2x, times the width, times the height. So all I need to do now is to say somebody to tell me what x is for different shaped boxes, and then I could quickly calculate what the volume was, because x is the only unknown in that equation for the volume. Now, if we change x, we can change the size of the box, as we've said. What value of x, though, gives the maximum volume? If you were actually using these boxes in some sort of manufacturing process, and you were generating loads of these boxes, and you wanted to put something in it like a liquid, it would be handy to know what the maximum volume was, so you could maximize the materials. To answer questions like this, we use differential calculus. So why do we use? One use of differential calculus is to find maximum values. And here is a definition of differential calculus. Any function, and what we've just written down is a function. Here it is. Volume equals 20 minus 2x, 12 minus 2x times x. That's a function to find the volume of the box. And what I'm saying here is that any function can be differentiated. So when we differentiate something, the process is called differentiation. So differential calculus involves differentiating something to give a new function. And I've underlined new because that's important, which tells us the rate of change or the gradient of the original function at any point. So how does this help us find the maximum volume of a box? Remember, that's what we're after doing, finding this maximum volume of the box. Well, let's look at a graph of the original function. Here it is, and that's the expression volume equals 20 minus 2x, 12 minus 2x times x. That's this thing here. All I did was to type that into autograph. Remember, autograph only recognizes y and x as the variables, so y equals 20 minus 2x brackets 12 minus 2x brackets times x, and you would get this function, you'd get this graph. If we look at it, what it's telling us is that as I change x, remember x is the height of the box, the volume is going to change. So if x is 0, then it's flat and there's no volume, there's no three-dimensional volume, so the volume is 0. As I increase x, the volume is increasing. And the interesting thing to note is that there is a value for x that gives us a maximum volume. Beyond that point, as I increase x, remember visualizing the box, it's now getting narrower and narrower and taller. The volume is going to decrease rather, until we get to this point here, where the volume again drops to 0, and that would be when x, or the base, is pretty well 0. Okay? So it's really tall, long, thin thing, and it's got no volume associated with it. Of course, as far as the mathematics is concerned, autograph will continue to plot y against x, and so what's happening from there onwards is x is now increasing, but the volume has now gone negative. So really, now we've left behind anything that's going on in the real world. And so this also highlights that something else which an engineer is often interested in is mapping this function and then understanding that actually really the only important part of this function is this bit. Beyond there, we're not interested in it anymore. So this is the bit of the curve we're interested in, this first part here, and there is a maximum value. How does calculus help us to find that? If we go back to this statement again, it says when I differentiate it, it gives me a new function that tells me the gradient of the original function. So if I were to differentiate this function here, I'd have a new function that tells me the gradient of this function at a point. What's the gradient when x is 1? That. If I drew a tangent to the curve at that point, that would be the gradient when x equals 1. When x equals 3, which is this point here, the gradient would be like that. It would now be a negative gradient. When x equals 4, a negative gradient again, slightly steeper. I could tell you exactly what the gradient at any point in this curve was by differentiating it, and as we'll see, the rules are very straightforward for doing that. And then I could say, what's the rate of change of the function at that point, the gradient? However, we're after the maximum value. What's interesting about the gradient when the volume becomes a maximum? It's 0, somebody said. Exactly right. If I find the gradient at this particular point, the gradient's 0. And that's something we often do with calculus. We find the differential of the function, which allows us to find the rate of change, and then we can use that to find maximum values, or, as we'll see later on, minimum values, because that's where the gradient drops to 0. So if I want to find the volume of this, maximum volume of this box, what I do is I differentiate this function, and we're going to look at that in a minute, and then I find out when that function is 0, because that's the point at which the gradients drop to 0, and that gives me my maximum value. And that's a very common mathematical technique to find maximum values. Differentiate it, and then find the point at where the differential drops to 0. And that's what we're going to do now. And that's a statement of it. So again, if you want to make a note of it,